So who all had a math class, basic classes here? Anybody had studied here, or like bachelor's math classes on algebra, right? So you have an idea of linear transformations and things like that. Okay, so I mean, so basic of what? So it's going to be a very basic class today, and I'm going to talk about what it means, the geometric intuition behind all the things that we do with calculations and matrices. Okay, so let's get it started. There is a nice quote actually. There's hardly any theory which is more elementary than linear algebra, in spite of fact of generations of professors and textbook writers has obscured its simplicity with matrices. Okay, so that's the whole idea of this lecture is to actually demystify things about matrices. Okay, I'm going to ask some key questions in here. And the essence of linear algebra, if we go in there, it's required for almost all disciplines. If you ask me what's the fundamental course if one should take in mathematics, I would say linear algebra. That's one of the most useful courses, be it doing computer science algorithms or doing statistics or electrical engineering or mechanical engineering. Matrices are the fundamental blocks. Okay, and so it's poorly understood by students. There are so many reasons for it. Most of them have emphasized the rigor of working with mathematics than matrices than what's the underlying geometric intuition behind matrices. So what are matrices? People who have done mathematics, what are matrices? Okay, let's see that what matrices are. Okay, so we might have probably learned so many crazy things, right? I mean, when you have two matrix multiplication, this looks like a very complicated formula. It doesn't even fit the screen here, right? You have two matrix A and B, you multiply that, A11, B11, blah blah blah, and so many difficult computations, right? Or you would have um, the formula for determinants, right? You have a determinant a11, a12, and you have this, and I mean, they would say that, oh, determinant of A is computed just by taking the product of the diagonals and then subtracting it with the product of the off diagonals, right? Or cross products, for instance, right? You know about cross products? Studied cross products? What are cross products? Or eigenvalues? You remember about eigenvalues? Computing eigenvalues? Okay, that's okay. So, there are so many things in here that are being taught in your elementary classes without even understanding why they are defined the way they are. Okay, we are vaguely aware of our geometric intuition behind such definitions, and you have to see that basically the numerical definition of computing and the geometric understanding will differ fundamentally. Basically, when you can ask something like, okay, compute this, and we can do it like blindfolded, right? I mean, oh, you take this, and but then they have a fundamental difference in our understanding. So while numeric understanding allows us to do actual computation, geometric understanding will help in judging what tools are useful for what problems. And they will also let you appreciate the problem better, right? And know how to interpret results. So a geometric intuition is always important. Okay? Like for instance, physics, right? I mean, it requires a geometric way of thinking, right? I mean, when you have a visually, when you can visualize something like, for instance, speed, right? It makes more sense to apply some formulae. So the geometric understanding underpins lots of things. It facilitates computations and it helps in applications, be it in physics or statistics or even doing data science and engineering. Okay, so it's very important to have the basics right and to have an intuition of and have an intuition and feeling of what we are doing here. Okay, so that's what I'm going to emphasize today. I'm not going to talk about anything really spectacularly difficult. I'm going to keep it at very basics so that we get the basics straight on what linear algebra and what matrices are. Okay, so without geometric understandings, right, most of them would look like wizards. Actually, for instance, if you're, let's say that you're taught from your young age that the formula for sine is this. Everybody knows the formula of sine is this, right? It's a Maclaurin series, right? X minus x cubed by 3, etc., etc. and you've been, let's say that you've been taught this is the formula for sine, and suddenly you're sitting in a physics class and you're being asked to do saying that, oh, this is this force acting downwards, right? It would all seem magical to you, right, without the understanding of geometry behind all these formulas, right? So it is important, right? I mean, it is important, but linear algebra is not too different actually. There are visual interpretations, intuitions behind the subject, and it's in fact it's more straightforward. Like here, it's very difficult to actually appreciate sine and the force that's acting downwards, right? But unlike in linear algebra, which is more straightforward, there have been so many things that the computation actually matches what you really observe, the geometric intuition, right? But actually, if you're in your classes, right? I mean, I wouldn't blame the professors. They would really try to make themselves clear, right? But most of the time, it gets complicated by textbook exercises and the rigor that follows and things like that. So we will try to understand the geometric intuition behind what we are doing, and that is critical whenever you're dealing modeling problems, when you're doing physical, when you're trying to construct physical examples, or if you want to do physics later on, everything, right? I mean, geometric intuition is important. So vectors, let's start with vectors. What are vectors? Bunch of numbers, right? Or some point in coordinates, right? So vectors, there are two main perspectives. Physics student perspective is a vectors is either a force, magnitude with magnitude and direction, right? That's a physicist view, right? As far as for a computer science, it's an ordered list of numbers. It's a bunch of numbers, right? I mean, it in program, in for instance in R, it has to be of the same data type, right? I mean, it has to be numbers or characters. But for a computer science perspective, it's just some ordered list of numbers, right? But whereas for a math student, right, it tries to generalize both these views. Both a vector is both, it has a magnitude and direction, as well as it's some bunch of numbers. So that kind of integrates, right? The later view comes at the fact that this both addition and scalar multiplication are extremely useful throughout linear algebra. These are two fundamental operations. Okay, so when you have, for instance, when you shine a torchlight on a pinhole, and then you flash another torchlight in there, the brightness is going to increase, right? I mean, the photons come, they are additive in nature. So these kinds of things, of course, there are some other things like interference and things like that. But in general, the addition and scalar multiplication are fundamentally useful things in throughout linear algebra. So in mathematics, we always think that a vector is rooted in some origin in two dimensions. It's a pair of numbers, right? It's associated for every pair of numbers in a coordinate. Let's keep it simple in two dimensions, right? Every point is a vector. So that is something that's fundamental. And vector addition is an extension of an 1D addition. For instance, you have this vector 1, 2, right? There is a vector here. And you have another vector 3 and minus 1. Okay. So how do you add these two? What does it mean to add two numbers? So you have you travel 1 units, and then you travel 3 units, right? You travel 5 units, right? Sorry, 4 units, right? So that's a simple addition, right? And that is extended here. And you have this, you travel here, and then you travel 3 units here, and then you travel negative 1 units here. So you land up here, right? So this is a natural extension of addition in 1 dimensions that you are taking it to 2 dimensions, right? It's done coordinate wise, right? So that's why in general you have this a coordinate wise addition. If x1 y1 is one set of vector, x2 y2 is some set of vector, it's x1 plus x2 and y1 plus y2. It's a basic simple addition, right? Scalar multiplication. Scaling a vector by a constant multiplies it, right? I mean, it's either squishes it or it extends it in some degree, right? And that is exactly what how it is defined. You have 2 times 3 and 1 a vector, and you multiply it, and you have 6 and 2, right? So this is a simple scalar multiplication. So these two operations, addition as well as scalar multiplication, are the defining features of what a vector is. Ultimately, if somebody asks you what a vector is, should be able to say that, oh, it is some set where addition and scalar multiplication is possible. That is what a vector is. Okay, from a mathematical perspective. So it doesn't matter at the end of the day whether it's a physicist view that you associate numbers, or you associate a list of whether it's magnitude or direction, or it's just some bunch of numbers, right? It's interchangeable at the end of the day. That is what it matters, and this gives data scientists also to conceptualize numbers in visual way, right? So these two different ways of thinking are synchronized, right? From an integrated perspective when you look at vectors, right? So it gives a physicist and graphics programmers a language to describe and manipulate space, and that can be crunched and run in a computer. So these two views of vectors are important, and that can be reconciled in one framework, okay? And that is essential, and that is the concept of vectors. Okay, so I mean, when you read about anything in like vector space, that's a technical definition. Anybody here who knows what a vector space is? Right? It's a space is nothing but a set with operations, and this operation is, you have two vectors that can be added, and it can be multiplied by scalar to produce another vector. Okay, these two fundamental operations. So these defines vector. This is, and it could have a geometric meaning behind it, or it may not. We don't. But then these are the fundamental technical definition of a vector. Although geometrically it makes sense, right? Linear combinations, span and basis vectors. So have you studied linear combinations? Linear combinations, let's do that. Okay, so this is a nice quote. Mathematics requires a small dose not of genius but of imaginative freedom, which in larger dose would be insanity. Okay, in two dimensions there are two special vectors, right? I mean, so one you can think of it as one in pointing in the x direction and the one that points in the y direction, right? And you can think of x coordinate as a scalar that scales this I vector, and a y coordinate is a scalar that scales the j vector. Okay, so you can think of there are two special vectors, right? So let's say that you have this is a I vector in one direction and j vector in another direction, and so you can think of any vector as a sum, right? 3 times I plus minus 2 times j. Have you been introduced to this notation? You know that I and j notation for vectors, right? So this is basically the notation for you can think of any scalar can be written as any scalar on the x-axis, right? Can be thought of as a product of product multiplied by this vector, right? So that's the, you can think of it as just a scaling, and then for y direction you can it's scaled by the j direction, the j direction, right? So you can think of, and these have a special name. These two vectors, they are called the basis of vectors. Okay, so I and j are two basis vectors. They define any other vector in that space. Okay, if you have another 5, you can scale I by 5 and you get 5. You go 5 directions on the x-axis, and you can scale j by 10 and you go 10 direction on the y-axis. Okay, and they define. So what if you choose different basis vectors? It need not be always perpendicular. You can choose some other basis vector like this, right? So initially we choose this, right? I is this and j is this. Instead we can choose two completely different basis vectors. Who stops us from choosing that? And so in that case, if you are using different basis vectors, right, the values of the coordinates will change depending on the basis vectors, right? So if you are having a vector here, let's say that 5 and 0, right? Now according to this, it's not going to be the 5 and 0, it's going to be different, right? Since you're changing the basis, right? So this values of the coordinates in the original will depend on the basis vectors. Okay, so that's what a linear combination is. If you have two vectors u and v, and a and b are any scalar, the au plus bv, this sum, right, it depends completely and defined implicitly on the basis vectors u and v, right? So that's why it's called a linear combination. You are adding, so it's a linear and it's a combination, right? So why is it so linear about it? Why it's called linear? You can combine, you can say that it's a combination of two vectors. What's so linear about it? So the thing is this, if you fix one of them, if you fix AU, right, and change B, right, it's going to form a line. If you just fix one of them and then if you move the other, right, it's going to form a line, and that's why it's called linear transformation, linear combination. Okay. Now, if you can allow both A and B roam freely, right, in the space, right, and so the resulting is called the span of the vectors u and v. Okay, so you can allow A and B to roam freely, right? Fixing u and v, of course, these are basis vectors, right? And so three things can happen. One is that u and v are zero, right? In that case, the span would also be zero, right? Because there's nothing happening there. U and v can be in the same direction. What would happen in that case? You have two vectors, both basis vector on the same direction, right? So what would happen in that case? It's going to be just one line, right? Right? I mean, the span will be just a line, and it could be in the different direction, and so the span would be the entire plane, right? So these three things can happen. That's span. What is the span of two vectors in three-dimensional space? What's that? Yeah, it's a plane, right? So it's a plane. So what about one more vector? If we can add a third vector in the same plane, we would be trapped, right? Right? I mean, because the span would still be in that plane, right? So we can't move anywhere. So there is another way of saying this. These are called linear dependence. Okay. So three vectors on three dimensions could be linearly dependent if 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 either one or two of the vectors is a multiple of the others. Okay. So I mean, you can think of it, if they all converge in a plane, they are linearly dependent, right? So that is the basis. The technical definition of a basis is this: a basis of a vector space is a set of linearly independent vectors that span the entire space. Okay, so that's the basis definition. That gives you, if you have any vector, you will be able to express that vector in terms of the basis vectors. Okay, so why does this definition make sense? Why the basis vector definition makes sense? Because you would collapse otherwise, right? You could collapse the entire two-dimensional plane into a single line. So a basis is a linearly independent set so that it spans the whole space. Okay. Linear transformations. What is a matrix? It's a movie. Actually, I like the movie. Did anybody watch? You like the movie Matrix? It's one of the finest movies, right? It's actually, the matrix is that actually linear transformation at the end of the day, right? I mean, it's essentially a function. What is a function? What is a function? Function is something that you have an input vector and it spits out another vector, right? So arbitrary transformations need not be linear. Okay, so for instance, let's take this, right? This is a plane, and let's say that there is a transformation, there is a function. So there could be a point here, and after the transformation, it could just go into another line here. So it could have an arbitrary kind of a transformation, and these are not linear transformations per se. Okay, the key word is linear, which means that all lines should remain lines. Okay, it should not be transformed into curves. A line should remain as a line, and the origin should be fixed. Okay, so the previous example was not a linear transformation. How about this? This is absolutely not a linear transformation, right? So since the origin here, right, I mean, it could move depending on how the lines are transformed, right? So that's not a linear transformation. So for in this case, right, the transformation is all these lines are parallel, but the origin moves here. So this is not going to be a linear transformation as well. So how about this transformation? Is this a linear transformation? The line should remain lines. So let's say that this is the white coordinates or the original, and after transformation you have the blue lines. So all lines should remain lines, right? Do you think it's a linear transformation? The lines are remaining as lines, right? But actually if you draw a curve, right, and the origin is fixed, but if you have a curve, it's not really remaining as a the diagonal line is not actually kept as a line in this transformation. After that it turns out to be a curve, right? So one of the key properties of a linear transformation is that the grid lines should remain parallel and evenly spaced. It should remain evenly spaced. That's one of the key characteristics of a linear transformation, is that if you have a grid line and if you're forming the transformation, it should be evenly spaced and the origin should remain fixed. Okay, so for instance, rotation is an example of a linear transformation. You can rotate through the axis, right? Like a 90-degree rotation or a whichever degree rotation, it's going to be a linear transformation, right? So how do we describe these transformations numerically? How do you describe these transformations? Is there any way you can describe these transformation? But interestingly, you don't have to be really worried about it, because once you know where I and j transforms, the basis vector transforms, you will be able to find out where any point would land on, because they are basis vectors. So any vector, right? Let's say that there is a vector minus 1i plus 2j, right? And if you know how I and j are transformed, you just need to multiply by I and j, right, to know where the point lands on. You don't have to worry about where every other point goes. All you need to know where I and j gets transformed, right? So once you know this transformation, you can find out where the new vector is going to land. Here, for instance, let's take this. The I is landing on 1 and minus 2. The j is transformed into 3 and 0, right? So this vector minus 1i plus 2j will be transformed into minus 1 times 1 and minus 2 plus 2 times 3 and 0. So it's going to be transformed into the location 5 and 2. Okay, so this is for any arbitrary vector. If you have I transformed into 1 and minus 2 and j is transformed into 3 and 0, I and j, x and y, any point will be transformed into x times 1 minus 2 plus y times 3 and 0. Okay, so that's what you need to know where the transformation takes. All this says that two-dimensional transformation is just made of two sets of numbers. One set of numbers that describes how I changes, the another set of numbers that tells you how j changes, right? So it's elegant to package these two where they land, right, into set like 1 and minus 2 and 3 and 0. This is all matrix is all about. Matrix is nothing but a linear transformation. Okay, so if you have some bunch of numbers, even could be gene expression data, for instance, right? What does the rows and columns, what does the column represent? It represents where this new gene is going to go, right? The values of those new genes are going to go. So matrix is often, and it's often written like that. I mean, if anybody asks you what a matrix is, from a more enlightened point of view, it's just a linear transformation. It's where the I and j lands on, the unit basis vectors lands on, right? So if you want to know where an arbitrary point P lands, you have to just multiply where the number I lands and where the number j lands. So you will get it. So it's a matrix vector multiplication is nothing but a transformation of points. Okay, from a geometric point of view, it's just you're just multiplying, transforming those points. Okay, so there are some special types of transformation. For instance, rotation, right? You are rotating by 90 degrees counterclockwise. All you're trying to do is taking this. This is where I lands on 0 and 1, right? It's going to be landing here, and minus 1 and 0, right? And then you're transforming. It's going to be a 90-degree counterclockwise rotation. And similarly, shear is, you have this, you're transforming, the I remains as 1 0 and the j coordinate is just moving to 1 1, right? So everything is going there. So it's a shear transformation, right? So what happens if the columns are linearly dependent? If one column is a multiple of another, right? 2 and 1 minus 2 and minus 1, right? It's going to squish, right, the entire plane into the whole into this line, right? So if the columns are linearly dependent, then it's going to squish into a one line. So linear transformation are actually, they are a way to move around the space, right, where the grid lines remain parallel and evenly spaced. Okay, so the origin goes to origin. This is the characterization of linear transformations. So these transformation, at least in two dimensions, can be described through bunch of numbers, right? Two sets of numbers. And matrices give a language to describe these transformations. Okay, so matrices or transformations. So that's the goal of. And a matrix vector multiplication shows where the vectors land after you do the transformation, right? Every time you see a matrix, you can interpret it as a certain transformation of the space. And this is a very critical idea to understand linear algebra. Okay, so this is a very fundamental idea, matrix and linear transformation. Now the movie makes more sense now. All right. So as a technical definition, right, this is what they say: a mapping L from a vector space V to vector space W is called a linear transformation if two vectors blah 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 L times U plus EV is this. This is a technical definition, but what this L means is a matrix. Okay, matrix multiplication and compositions. Let's go to that. So this is a nice quote by Emil Artin, who is one of the famous mathematician. Almost all proofs of involving matrices can be shortened by 50% if one throws the matrices out. So one of the things that you may want to see when you have a matrix is that once you know that it's a transformation, right, one can apply one transformation after the other, right? You can do a rotation plus shearing, or you can do a shearing plus rotation, or there could be other transformations that you may want to do that, right? And the resulting will be, think about it, if one leaves your grid lines parallel and evenly spaced and you're applying the other, it's going to remain parallel and evenly spaced, right? And so these two transformations can be applied in sequential way, right? Shearing plus rotation, right? The new transformation that happens is called a composition of transformations. It's just like composition of functions. You have two functions, you can compose one with the other, right? One goes from here to there and then. So it's the composition of transformation. So you have the shearing and rotation, and what you have the composition function. So this composition is technically known as matrix multiplication. Okay, so all this says is that you know where this I and j hat lands, and after this you know how this lands. So when you multiply, you know where the new landing point of I and j is, right? The new matrix. Let's compute the composition of where does I go here. Let's say that you have the matrix M1 and the matrix M2, right? So you know from M1 where does I go in M1. 1 1, right? And j goes to minus 2 and 0, right? So what you can do is m2 and m1. So I goes to m1 and 2. So you multiply this m1 and m2. So this is just given by 1 times 0 1 plus 1 times 2 and 0, right? So this is 2 1, right? And similarly, you know where the j goes, right? So you have to multiply the minus 2 and 0 with this, right? And so that in general, that is how it is, why it is given this complicated formula of matrix multiplication. It's just the composition of where the point is going to land, right? So you take, this is where the I goes and this is where the j goes. So you can immediately refer or infer how matrix multiplication behaves instead of thinking about that complicated formulae, right? So it just really represents applying one transformation on another, right? It doesn't matter whether, but it matters whether if we apply shear first or rotation first, right? I mean, it depends on how you multiply two matrices. In general, the composition is not what is known as commutative, right? If you apply rotation and shear, it's not same as applying shear and rotation. right? That is why matrix multiplication is non-commutative, right? Now think of associativity. You can apply a matrix M1 to M2 and M3. Is it same as applying the matrix M1 to M2 and then to M3? It's trivial because it's just a composition now. In terms of geometric, it's you don't really have to compute all those nitty-gritty details of this. Think about taking all these and multiplying and making it as a mess, but thinking about geometrically, it makes more sense for matrix multiplication, right? So these so far we have just described in 2 dimensions, but it equally applies to 3 and higher dimensions, okay? So we will not go over higher dimensions or infinite dimensions and things like that where things could get really complicated. Okay, so we will stick with basic finite dimensions. It's fine. Determinants. How many of you know what determinants are? You know how to compute determinants? Determinant of a matrix. You know, okay. Yes, the purpose of computation is insight, not numbers. Remember. Richard Hamming. So some transformations, right? The same language of transformation, some transformations stretch the space, but some of them squish. Okay. So for instance, let's say this transformation 3002, right? What does it do? It takes I to 3 and 0. So it takes here and j to 0 and 2. It expands the space, right? Some of them can squish the space, right? So the area is a good measure to find out how much a space is squished or how much it is expanded. So for instance here, right, the area, unit area, right, it's expanded, right, to encompass this. So the new area is what? 3 times 2 is 6, right? This is the new area, right? 3 and 2, this is the area of a square, right? Whereas for a shear, something like this, 1011, right? The area remains fixed, right? Although the area remains because it's the distance between the grids remain the same, right? So for a shear, it's fixed. So even though the shear transformation appears to squish things, the area remains the same, right? And one of the nice things is that if you know how one unit square changes, we can know how every area changes, right? Because it's all transformation. They leave the grid lines parallel and evenly spaced, right? So if you know how one area changes, you will be able to find out how any other area changes because the lines should be parallel, right, and evenly spaced. So the same this special scaling factor, right, how the area changes according to a transformation, it's called a determinant. Ultimately, that's what determinant is all about. So you have a determinant of a transformation, right? You have how actually transformation shapes, how makes it the area bigger or smaller is what a determinant of a transformation, of a linear transformation or a matrix for that matter. Okay. So for instance, the determinant of a transformation is 3 if it increases the area after transformation by 3, right? I mean, so this is the 3 times you will get the 3 areas 3 times, right? A determinant of a transformation is 0 if it squishes, right? Think about a transformation, linear transformation. If it squishes into a line, all the area is going to be condensed into a line, right? So it's going to be 0. So this is a pretty important concept. So to know when a determinant is 0, right? Because it will reduce all the points into a line, right? So far that's a very pretty important concept. So you will know once a determinant is 0, if you are given a matrix and you are given that it's a determinant is 0, that means that the area is it's squished into a line. In case of 3 dimensions, it could be a plane. The volume would be squished into a plane. Okay. So whatever we said about determinants is so far a positive quantity, but determinants can also be a negative quantity. Okay. So you have to see what it means when determinant is negative. And with this, the idea of orientation of space. Okay. So you say that the j is to the left of I, right? But if doing by some transformation, if if the direction is reversed, so for instance here, L of I, the transformation leaves this I here and then the j is flipped so that L of j is to the right of I, right? For such transformations, the determinant is going to be negative. Okay, so still the absolute value will tell us how the area has changed, but the determinant is going to be negative. For instance, another way to think about it is like this: you have a linear transformation, and you slowly change it, right? First it will have some area, right? And slowly it will have, suddenly the I is going to be changed to this direction, so that it will be 0 here, it will be 0 at this point, and then it will go into negative, right? So you can slowly transform. You can see that when the direction changes, immediately the determinant is going to be negative. Okay, so this idea of determinants representing this area extends to 3 dimensions as well. In this case, we will have parallelepiped instead of a parallelogram. Okay, so a 0 volume means that the entire parallelepiped gets squished into a 0 volume, meaning that the vectors would either lie in a plane or it becomes a single point. Okay, it also means that the columns of the matrix are linearly dependent, right? One will be the multiple of another because it's going to lie on a plane or a line, right? So in 3 dimensions, what it means to have a determinant negative, right? You have do you know the right hand rule and the left hand rule? How do you determine the coordinates? So you have the I vector here, J vector here, and K vector here. And so if the direction is reversed, that you will not be able to identify the axis, you can do it only through your left hand, then it means that the negative determinant. But still, the area would be determining the volume of the parallelepiped. Okay, so that's important. So how do we compute determinants? You know how to compute determinants? You have a determinant of A, B, C, D, right? This is a nice visual to do that. See, if you think of A, B, C, D as this, you can immediately see that the area of this parallelogram, right? It is going to be, the whole area is what? A plus B times C plus D, right? And you are subtracting 2 BD, so 2 times BD by 2, which is BD, and you're subtracting 2 times AC by 2, and you're subtracting 2 times BC, right? It's AD minus BC. So this is a nice way of seeing why determinants mean area, right? Inverse matrices, rank, and null space. These are some of the concepts that you will come across when you study linear algebra. Okay, several linear applications come in the form of solving linear equations. Almost all, when you are solving some complicated differential equations, you will try to linearize it, and then everything could be, almost everything could be approximated as a linear system. Okay, so in the case of nonlinear equation, they can be approximated by linear equations to a good degree. So linear algebra is very useful for solving such applications. So in general, you have 2 systems of linear equation: 2x plus 2y equal to minus 4, 1x plus 3y is equal to negative 1. Okay, you can think of solving it as a matrix, right? You have a matrix, you have a vector x, y, and then you can solve for v. So right, so what does this mean? The transformation: find the original values of the point where it maps after the transformation, right? Let's say that I goes to 2, 1, minus 1, j goes to 2 and 3, right? And the final landing point is minus 4 and negative 1. What was the original point, right? So this is a way of looking at it from the point of view of linear transformations, right? So the solution would depend on how A behaves, right? Whether it squishes all the points to a line or not, right? So the determinant would determine the solutions of these equations, right? If it squishes, the area would be 0, right? So for every transformation, we can apply the inverse of the transformation. Okay, so if you're rotating by clockwise, you can rotate it by anti-clockwise. Okay, if you're doing a shear, you can do a reverse form of shear, right? So the result would leave the vectors intact, right? It should leave the vectors in the same place. And you can use that trick to find the solution of this, right? You just multiply by A inverse and you would find the original vector, right? So that's an inverse transformation that you can apply. So when the determinant of A is 0, the space is squished and there is no inverse, and we cannot unsquish a line to make a plane, right? It's just going to be a line. So the same happens in 3 dimensions, and there is a name for different types of 0 determinant cases, right? This is called the rank of a matrix. Okay, the rank of a transformation is a line, we say that it has rank 1. If the output of the transformation is a line, we say that it has rank 1. In 3 dimensions, if it's a plane, we say that it's rank 2. Okay, rank means the number of dimensions in the output. You have a transformation, you are transforming. What's the output space, right? The set of all outputs for the transformation is called the column space of the transformation. You can multiply and you call the column space of the transformation, and it is a span of the columns. If you think about it, it's just a span of the columns, right? If the span equals the full space, the transformation is called the full rank. Whenever people say that, oh, it's a full rank matrix, it means that you have to think that it spans the whole space. Okay, so the zero vector is always included because the transformations leave the zero into the same place. It's not going to move. So no, any non-full rank transformation, there could be entire range of vectors that could go into origin, right? That could be mapped to the origin, that could be squished. In 2D, right? If there is a transformation, the entire bunch of vectors can be, a set of vectors could be mapped to the origin. Okay. In 3D, if there is a plane, there is a bunch of vectors that will be squished to the origin. And if it squishes to a line, the entire plane is squished to the origin. You have to think about how in 3 dimensions, right? It could be squished to the origin. And that is called a null space of a transformation. Okay, null space is a set of vectors when you apply a linear transformation, how it's squished to the origin. That's called the null space. Okay, it just means that the set of vectors becomes null or becomes zero after the transformation, right? So non-square transformations and eigenvalues and eigenvectors. You know, there was a one famous quote that, you know, on a quiz I asked you to find a determinant of 2 by 3 matrix, and some of you, to make great amusement, actually tried to do this. You can't really find a determinant of a 2 by 3 matrix, can you? Because determinants are for square matrices, right? So what happens in 3 dimensions? You have, so far I told you about 2 by 2 matrices. What about 2 by 3 matrices? And what about 3 by 2 matrices, right? So these are actually, you can, it's similar. What you can have is you can map to the same thing, right? A vector ij can map to a point in 3 dimensions, right? So that's what all it means. All we should have is the grid lines should remain parallel and evenly spaced, and origin should map to the origin. And once a transformation is maintaining these two properties, it doesn't matter what the space is. It could be a 2 dimension to 2 dimensions or 2 dimensions to 3 dimensions. Okay, so for instance here, right, 2 minus 1 minus 2, this is where the I lands and this is where the j lands. So you can have a transformation from 2 dimensions to the 3 dimension plane, right? So if a matrix has a full rank, right? So for instance, in this, you have a 2 by 3, in this, this matrix has a full rank because it spans the entire 2-dimensional plane, right? So it's a full rank, right? Because you can still talk about ranks when you have a non-square matrices, right? So what does a 2 by 3 matrix mean in this context? What's that? Yeah, the previous was 3 by 2, right? So what does 2 by 3 mean? Yeah, from a more transformation point of view. Right. So basically, it means that it just means that a 3-dimensional vector is mapped to a 2 dimension. So the I, j, and k are mapped in the plane, right? So it just means that the 3 dimensions is mapped to the 2 dimensions. I mean, 3 vectors in 3 dimensions is mapped to 2 vectors in 3 vectors in 2 dimensions. Yeah.
The determinant of that 2 by 3. There's no determinant.
So yeah, so for
because it's flat and there's no volume to it.
So think about it. When you have dimensions from the same dimensions, you can see how the area is mapped, right? But what it means when a 2-dimensional vector is mapped to 3 dimensions, the area, you can't really associate an area associated with that, right? I mean, in 2 dimensions, you can say that, oh, this area has changed to that area. But here, it changes from an area to a volume, right?
Is it then volume to element because it's a 2 by 3? That is
So here the input, so the input is 2 dimensions, the output is 3 dimensions.
Yeah,
So
it's a 3 by 2.
yes, for the 3 by 2 case, right? For the 2 by 3 case,
Yeah.
the input is 3 dimensions,
Right.
the output is 2 dimensions, right?
So that's no volume because that's flat.
Yeah, but yes, that's like, yes, the association between the volume is not preserved because you have a volume, right? And you have an area here. You can't really make an association between a volume and an area like you can make between areas and areas. Oh, this area has changed to this area. 2 units of land has been changed into 5 units of land. That's fine. Okay, but 2 units of space as mapped into 5 units of land is doesn't make any sense. You know what I mean? So you can't really map from I mean, you can't really make sense of area preservation when it comes to 3 dimensions to 2 dimensions. So that is what essentially means. Okay. So as far as eigenvalues and eigenvectors, I thought I should present, but there is a much better presentation and there is a much better resources for linear algebra. Okay, this guy does it amazingly well, and I thought I will let him speak than me speaking. So this eigenvalues and eigenvectors. This is one of the fantastic videos, and I will tell you the resource where you can go and watch the entire series. Okay, so let's see. There is no volume here. Oops, what happens to volume? Do you know how that works here? Oh. Do you know if this would work from the TV? I don't think it works.
There should be a drop down to say which audio source you want to use.
Which audio source I want
Because
to
it's whether you want to use your laptop or you want to use the.
Oh, from here?
No, from your settings.
Oh, I see. Okay. System preferences?
Yeah. If you go audio.
Sound?
I'd assume so.
Okay.
Output. Oh, it's telling it to use the HDMI. So
Yes.
That's strange that it's not playing sound.
It's not playing here?
It should. I don't know why it's not. It doesn't go through the TV.
Does it?
Otherwise, you can change it to use your laptop speakers.
Oh, in that case, I just need to take.
You wouldn't just go back to the output setting and just change it to the internal.
Okay, okay. Let me try that then. I think that might possibly. System preferences, sound, okay, it should now speak from this. Oops.
If you have a solid visual understanding for many of the topics that precede it. Most important here is that eigenvectors and eigenvalues is one of those topics that a lot of students find particularly.
Can I use, there is a direct computer that I can use from here?
It's the room that's got sound. That's what the other HDMI should be going through. So I don't know why that's not making. You should be able to use the computer.
Oh, the. Okay, let's do that then. I think that would be